Frequency hopping has long been used in military and high-security radio applications. Frequency hopping is a common technique in communication systems to improve security. It makes signals harder to jam, and due to constant movement, often based on pseudo-random sequences, it requires a jammer to have knowledge of hopping patterns. It creates resistance to interference and allows users to leave busy frequencies and transmit on frequencies with less noise, increasing data rates. It also makes eavesdropping more difficult, requiring an eavesdropper to lock on to the frequency hopping pattern used by the user. ZTX set out to implement frequency hopping in 5G. After significant development in frequency hopping techniques, it was determined that without alteration to the 5G standard, this was not possible. As a result, UE hopping was developed to create a pseudo-frequency hopping that would be compatible with any device. The block diagram shown is the UE hopping block diagram. In UE hopping, we take advantage of the fact that UEs in 5G are often allocated by the base station to different frequency bands. We then use an external device to determine the state of each device and send the signal on the best quality UE connection. Even when UEs are allocated to the same band, differences in interference and connection quality between two users still make UE hopping useful. You can see in the figure we have a high priority and a low priority message. An external device uses the state of the UE connections to determine how to route this message through UEs. To obtain channel state information from the UEs, we use AT commands, or attention commands. This is because the information available at the Android application level is often very outdated when compared to AT commands, which directly query the modem on each UE device. We use the AT commands to obtain each device signal to interference noise ratio, or SINR. SINR is a popular metric in communication systems that quickly gives a description of signal quality. Using the SINR, the messages are then appended with a bit. This bit indicates whether they came from a high-quality source or a low-quality source on the receiver side. The receiver then uses this bit to assemble the message. This simple idea of sending the important message through the important link vastly decreases bit error rate of the high-quality link and lets us send messages in environments that could normally not allow messages to be received. UE hopping is simply choosing the better link and sending the more important message through that link. This simple technique allows for the advantages of frequency hopping on devices that would normally not allow this technology. It allows for implementation entirely at the application level and requires little to no modification on any layer below the application level. This makes UE hopping able to be implemented on any modern 5G device with little to no modification. It improves data rates, reliability of received messages, and makes the high priority message resistant to jammers. It also makes eavesdropping difficult. In essence, it acts as a pseudo frequency hopping, which is compatible with the current 5G standard. To accomplish this goal, we created an Android application. The application uses peer-to-peer communication. We use peer-to-peer communication to ensure security between users. Peer-to-peer eliminates the need for a centralized server, which facilitates messaging. To accomplish this goal, a library called WebRTC was used. WebRTC is an open-source peer-to-peer communication library maintained by Ericsson and Google. Servers are used to establish the initial connection, called signaling servers. But after this, communication is purely between users. Most of the time, directly, without the use of some sort of relay server. Although relay servers are used as a fallback when negotiation between peers fails. A laptop is connected to each UE using a USB. This USB is used to send the attention commands to the modem of each UE device. This information is then used to route the messages to the receivers. Finally, Wi-Fi direct connections are used to facilitate communication between the laptops and the UEs. The laptop acts as a pseudo AP and sends UDP packets directly to the UEs. The UEs then act as simple relays and send these messages over their established WebRTC link. Next, we will show a demonstration of the technology, demonstrating its effectiveness. Firstly, we show the screen of the sender. On the right side of the screen, there are 6 buttons. I will highlight the function of the important ones. Firstly, the Browse Files button. This lets us select the image we are going to send over the link. The Clear button clears the selected image and lets us select a new one using the Browse Files button. And the Send image lets us send messages over Wi-Fi direct to each UE. Next, we can see what's connected to the laptop. The UEs are connected to the laptop using USB. Again, when we click the Send button, it sends the image over Wi-Fi direct to each UE, and the program sends AT commands through the USBs, sampling the SINR of each UE, and sends the messages to each UE over the Wi-Fi direct link based on this information. The UEs then send that information to the receivers on the other side. Next, we can see the receiver. You can see that the image sent from both the low quality and high quality link is displayed side by side. Right now, each one is identical. This is because the connection quality is roughly the same for each UE device connected to the laptop. For the next demonstration, a Faraday bag is used. This bag greatly degrades the signal quality of one of the devices. For those of you with knowledge on EMC, normally this cable, which is going into the bag and connecting to the device, would break the EMC seal of the bag. To minimize this effect, a ferrite bead and coiled cable is used on the UE, which causes the seal to remain mostly in effect and degrade the signal quality enough to prevent the packets from reaching the receiver. Assuming everything is working correctly, the laptop should select the device with the high quality link, or the device that is not inside the Faraday bag. The message should then be sent over both links, but the only one that is received should be the high quality link. We can see here that the receiver, after the program has played out, has received both messages. However, the one received from the low quality link has too many errors and is not able to be assembled by the program. As such, only the high quality link image is assembled. This clearly demonstrates the effectiveness of UE hopping and shows its resilience to interference and malicious jamming, as well as its ability to be used on standard 5G devices. Thank you for listening to this presentation.
Thank you for watching.